Finding limits from tables. So we've already used tables to evaluate a limit in a few videos ago, but here we're going to talk about it a little bit more and do a couple more examples. So the thing about tables is that tables always work. They always work when we are trying to evaluate limits, since tables allow us to look at the behavior of a function, i.e. the height or the y values of a function, around a certain input or around a certain x value. Because again, we said a limit is the tool that allows us to look at the behavior of a function. So again, tables will always work. Now, using tables to evaluate limits is known as a numerical approach because all we're really doing is we're just plugging in numerical values into the function and analyzing some patterns that come out. So again, numerical approach. That's not something you need to know, just in case you're doing some reading or you hear it somewhere, you'll know and be familiar with that term. Alright, so here we want to look at our first example. We want to find the limit as x approaches 1 of the square root of x minus 1 over x using a table. And if we notice, we're looking at the limit as x approaches 1. Not x approaches 1 from the left, not x approaches 1 from the right. So therefore, this is a two-sided limit, which means we need to analyze both sides, which is why you can see on the screen that there is a table for the left-hand side and a table for the right-hand side. So we do want to analyze the behavior on both sides, make sure they meet, and then figure out that actual value. Now, to do this, we do need to choose numbers. So to choose numbers, I always find it helpful to draw a number line. And in the middle, I'm going to put my a value, which is 1. Alright, first we're going to tackle the table from the left-hand side, so I need to pick a number that's close to 1. That's also a little bit less than 1. Now, there are a lot of these numbers, because 0 would work. 1/2 would work. 3/4 would work. But we want something a little bit closer, so we're going to start off with 0.9. And we'll fill that into the first row. Well, now we need to pick something a little bit closer. Alright, well, 0.9 works, so something a little bit closer. What if we just add another 9? So 0.99. And we can do that again to get 0.999. And then one more time for luck, 0.9999. And as we can see, that is pretty close to 1. And I wrote 1 instead of a 9. Interesting how that brain works. Alright, so now we need to choose our numbers for our right-hand side. So again, we're looking for numbers that are still close to 1, but that are larger than it. So following in a similar way to picking 0.9, we can then come over here and we can pick 1.1. Because 1.1 is larger than 1, but it's also only 1/10 away. Now here's a trap that students sometimes fall into. They try to mimic the same pattern for the left-hand side. So they come in here and they say, oh, well, the next one is 1.11. And well, technically 1.11 is 1/100th larger than 1.1. So 1.11 would actually fall farther away from 1, not getting closer to it. So you don't want to fall into that trap, because that will not work with the right-hand side here. So we need to kind of follow a different pattern. So instead of 1.1, let's get a little bit closer with 1.01. So now we're just adding zeros. So we can get a little bit closer with 1.001. And a little bit closer with 1.0001. And there we have it. We have all of our input values that we're going to throw into our calculator. And when I say throw into our calculator, we're going to throw it into our function. Now you can do this individually, or I would recommend using the table feature on the calculator. And then if we actually throw in these x values, let's see, when x equals 0.9, we're going to get 0.51317. For 0.99, we're going to get 0.50126. And then 0.50013. And then 0.50001. All right, so then from this table, if we look, as our x values get closer and closer and closer to 1, it appears as though our heights get closer and closer and closer to 0.5. So therefore, we can say the limit as x approaches 1 from the left, because that's what this table represents, of f of x is going to be 0.5. From here, we need to look at the table from the right-hand side. And again, we're going to see that if we fill in these numbers, will the f of x values match the 0.5? So, plugging in 1.1, we're going to get 0.48809, and then 0.49876, 0.49988, and 0.49999. And it would appear that as our x values get closer and closer and closer to 1, or as x approaches 1, our f of x approaches 0.5 as well. So therefore, the limit as x approaches 1 from the right of f of x also equals 0.5. And as we can see, these two limits are equal. So we have the high five. Therefore, the two-sided limit exists. So we can say the limit as x approaches 1 of the square root of x minus 1 over x minus 1 is 0.5. Boom, done. Evaluated that limit using the table. All right, let's take a look at another one. So this next one, we have the limit as x approaches negative 3 of 3x plus 9 over x squared minus 9. And again, we want to evaluate this using a table. So, just like before, I'm going to draw the number line. If you find it helpful, please go ahead and do it. However, if you don't need the number line, do not feel as though you have to draw it. And just like before, I'm going to put my a value, which this time is negative 3, in the middle. Now, these are a little bit different because our x values are negatives. And negatives kind of, they flip things around. So, looking at the left-hand side first, we're going to want to find numbers that are less than negative 3. So that means we're going to be looking on this side of the number line because it's less than. And that side of the number line goes like negative 4, negative 5, negative 6, negative 7. So, we want to pick a number that's less than negative 3, but also close to it. So, we'll pick negative 3.1. Because again, with the negative numbers, negative 3.1 is less than negative 3. And then we can get closer by going negative 3.01 and following a similar pattern for last time, except the sides are flipped. And then finally, negative 3.0001. All right, then, the right-hand side. We want to pick a number that's close to negative 3, but also greater than it, so we'll pick negative 2.9. And then we'll get closer, so negative 2.99, negative 2.999, negative 2.999, and 9. Alright, so now we have all of our input values, and as you see, this is kind of, I don't want to say the opposite, but our numbers, our patterns are flipped. Because on the last slide, we had the 0.9, 0.99, 0.999 on the left-hand side, and we had the 0.1, 0.01, 0.001 on the right-hand side. But, since our a value is negative, we have to flip it. Alright, but again, I'm just going to plug these into the calculator. I'm going to use the table feature, which spits out all the answers nice and easy. So I'm going to get negative 0.4918, negative 0.4992, negative 0.4999, and then for negative 3.0001, the calculator just rounds it up to negative 0.5. So therefore, we can say the limit as x approaches negative 3 from the left of f of x is going to be negative 0.5. And there we have our left-sided limit. Let's take a look at the right-sided limit. So when I plug these values into the calculator, let's see, negative 2.9 gives us negative 0.5085. That's a horrible 5 at the end. Let's try that again. Negative 0.5085, and then negative 0.5008, negative 0.5001, and negative 0.5. So therefore, the limit as x approaches 3 from the right of f of x is going to be negative 0.5. And now, just like the previous example, the limit from the left does equal the limit from the right. So huzzah, we are good to go. So therefore, the limit as x approaches negative 3 of 3x plus 9 all over x squared plus 9 is going to equal negative 0.5. Boom. Done. Solved. Alright, so now our next example is worded a little bit differently, and you might notice there's only one table instead of two. So let's investigate why that might be. So here we want to let f of x equals x cubed minus 8 over 4 times the quantity x minus 2, and we want to use the table to evaluate the limit as x approaches 2 from the left. So again, this one only uses one table, because we're just trying to evaluate this one-sided limit. So we only need one table here, and it is from the left. So I'm going to start off by drawing my number line here. Again, if that's helpful for you, please go ahead and do it. If not, don't worry about it. But I'm approaching 2. Again, it's a one-sided limit from the left, so I'm only looking at the left-hand side. So I'll choose 1.9, 1.99, 1.999, and 1.9999. And then we can put those into the table. And there you have it. We are approaching 2 from the left. Alright, so then we just need to throw this into the calculator and figure out what our f of x values are. Alright, so when I put in 1.9, I am going to get 2.8525. When I throw in 1.99, I'm going to get 2.985, and then 2.9985, and finally 2.9999. So as x approaches positive 2 from the left, our f of x, it appears, gets closer and closer to 3. So therefore, our limit as x approaches 2 from the left of f of x is going to equal 3. Done. Woo! Evaluating limits using tables. Not difficult at all, but it is a little time consuming to have to write out these tables all the time. Alright, so our last two examples are going to be dealing with tables, but the tables are already given to us. So we just need to look at the table and determine what the limit is going to be with the table. Alright, so here we want to evaluate the limit as x approaches 0 of sine of 1 over x squared using the following table. And let's see, we have x approaches 0 from the left-hand side, and then x approaches 0 from the right-hand side. So this side right here is going to be the left, so the limit as x approaches 0 from the left of f of x. And if we look at our numbers, let's see, we go negative 0.5 to negative 0.3 to negative 0.3 to 0.9 to negative 0.4 to negative 0.6. Well, those just seem to be random numbers. There doesn't seem to be a pattern here. Nothing's getting closer and closer to a specific height. It just looks like randomness. So, since there is no pattern of behavior here, it's just erratic, and there's other explanations for this that we will talk about later on in the course. But for now, the limit as x approaches 0 from the left does not exist because these numbers don't show any pattern. They just jump around. Well, then if we look at the limit from the right, as x approaches 0 from the right of f of x, it appears that our numbers do the exact same thing. There's no pattern. It's just some random number, some random heights here and there. So therefore, our limit from the right does not exist. So therefore, our two-sided limit, the limit as x approaches 0 of sine of 1 over x squared, does not exist. However, when you do these in the online homework, it's going to ask you to use the empty set symbol, which is the 0 with kind of the slash through it. Again, that's referred to as the empty set. And that's what that's the symbol Newton is using to represent does not exist. So therefore, using this table, we can see that the limit as x approaches 0 of sine of 1 over x squared does not exist, which means our function does not approach any specific height at 0. It's all over the place. All right, let's take a look at one more example. So here we want to evaluate the limit as x approaches 0 of sine of 3x over 2x, and we are given the table. And we'll do the same thing as we did in the previous slide. We'll first look at the left-hand side. So of the limit as x approaches 0 from the left of f of x. And let's see, we're going 1.477 to 1.499 to 1.49999 to 1.4999999. So here we can see there's a pattern. We're getting closer and closer and closer to one specific y value, with that y value being 1.5. And then looking at the right-hand side, limit as x approaches 0 from the right of f of x, we have a similar thing. We're getting closer and closer and closer to the y value 1.5. So in this case, the limit from the left equals a number, the limit from the right equals a number, and those two numbers are equal to the same number, so therefore our limit as x approaches 0 of sine of 3x over 2x is going to be 1.5. And there you have it, folks, evaluating limits using tables.